Good morning, everyone, and thank you for joining us for the second part, four-part series from Andy's principal architect, Dr. Thang Tran. If we had questions that came in during the course of registration, Dr. Tran will try to answer those during the course of his presentation. If we don't get to them all, we'll answer them in the question and answer session at the end. If you have questions, please enter them into the chat window, and we'll take them in the order it was received. Without further ado, Dr. Tran.
Hello, everyone. I'm Thang Tran, and this is the second part of the four-part series where we will go to the details of the RISC-V vector extension ISA. Okay, the basics of vector extension ISA will be discussed today. I will try to answer some of the registration questions throughout the presentation. All the questions will be answered in the next webinar sessions. For example, we will have comparison to Fujitsu A64FX and examples, including matrix multiplication to specifically take advantage of Andy vector processor, and this will be in the last webinar. Okay, so I will show this slide on every presentation, and it basically, these are the terminology and the abbreviation that we use throughout the presentation. And so the most important thing today would be the SEU is the element width, the vector raster length in bits, and the raster grouping. VL is the application vector length, and VL max is the vector length, the number of maximum element. Okay. So let's go to the basics. So vector raster ISA, it is the vector raster operation. So all the vector operation are between the vector raster, except for low store, and this is the basics of the RISC concept. Only the low store instruction access the memory. All other instruction are basically raster only instruction. This is in contrast with some other vector memory ISA, where all vector operation are on the data memory. Okay, and so the basic requirement is that the vector data raster hold n element of n bit length, and each element had the n bit y. And so for SEU, a single vector element is n bit, and it's the power of 2. And then the vector length is basically a multiplication of the number of elements with the element width. And all had to be in power of 2, of course. And VLEN had to be greater than the SEU. VL max is the number of vector element n, and it's basically the VLEN divided by SEU. So all elements are supposedly independent executed, mostly except for the permute instruction. And we also have a vector control raster called a mask. The mask is basically a predication to indicate whether so we have 1 bit mask for every element of whether to update the element or not. And we use the vector raster 0 for the mask. And so, of course, the vector instruction have all the compute instruction, and it including the mask and the permute. The vector low store unit, it basically would handle the low store, and the low store, there are 3 basic type of version is with stripe, with index, and the segment low store. Okay. These are the parameters that Andy support other company may decide to support different size or subset of the instruction. And so the scalar, it basically is the RISC-V ISA, it's a standard scalar RISC-V ISA, and then you have a floating point. And for the vector, there's a vector ALU that basically handle all different type of functional unit we have, and it operate on side or unside or floating point. And the element width is from 8 to 64, and the operation can be between vector and vector, vector and scalar, or vector and integer. And of course, for fixed point, you have saturate and overflow. Then there are mask, and each element can be masked or unmasked. Then there's a vector memory, basically low store instruction. There will be side and unside. And the memory width, the element memory width can be from 4 to 64. And so the integer 4-bit is actually a custom instruction. And the 16-bit also include a custom bflow 16. And then the operation width, again, it's the same as this, would be from 8 to 64. And when you do the low store instruction, it can be, this basically strike, the constant, index, and segment, and every element is also masked and unmasked. So at Andes, we started with the VLEN equal 512-bit. Then we added 256 and 128-bit at later. So throughout the presentation, I'm going to use a 512-bit at the example. And so, okay, and the notation. So for the vector, you would have VS, it will, all the rest, it would start with the V. And for scalar, it will be R, and then for floating point, it will be F. So these are source, and this is the destination. And the rest of the number, again, it will be V0 to be 31. For the scalar, it will be X0 to X31, and then you have F for floating point. The note here, X0 is not a real raster. If X0 is used for source raster, then it means that the data is 0. If it's used for destination raster, it means there's no write back. And V0 is also can be used for vector mask and also used for carry bits. Okay, so the basic overview, there is a memory, the vector low store unit, and there are two raster file. So we only talk about vector raster today, so I'm not including the floating point in this figure. So there are vector raster file and a scalar raster file, and then there's all the functional unit. Now, memory. So many type of memory can be implemented with the Ande vector processor. So we have cache, uncached, and local vector memories. Ande processor can support 8 concurrent low store from 3 different type of memory. We can work with customer to basically on the memory subsystem. For instance, you know, the L1 cache can be 1 megabyte size. For all the read and write port to the raster file, actually it's a centralized control for all the read and write port. And the raster file is therefore data dependency, it is handled by the scoreboard. So it is somewhat difficult to decouple the vector processor from the CPU because the vector instruction have many reference to the integer raster file, like read and write to the scalar for the vector operation. And it's also the scalar raster file is also used for the address for the vector low store. So it requires some work to actually to decouple the vector processor from the scalar. And so it requires a lot of work actually. So it is hard to decouple them. And then we have 8 functional units. And a side note here that the functional unit, the way we design it, it's very flexible. We can actually duplicate the functional unit as needed if you have some instruction that require to have a lot of floating point MAC operation. We can actually duplicate the floating point MAC unit. And we can also add custom functional units or hardware accelerator, if you call it, to the vector functional unit. Okay, so now we go to the basics of the ISA, and the first thing to understand is the control and status register, which is very important. And so these are the vector CSR register. And so there are 2 types. One is basically for the arithmetic instruction. So you had a saturation and routing mode for the arithmetic calculation. And then the other register, the control register that are very important is the vector length and the V type. Okay. In normal implementation, when you write to a CSR, it is normally a serialized event, which is very slow. And so VL and V time actually can change very frequently in the code. So all the vector instruction had to use a speculated copy of VL and V type. So when you update the VL and V type, they are not a serialized event. They actually just like a normal instruction. Okay, so the fixed point register. So you have the saturation flag and the routing mode, and it can be merged into a single register to have both of them into a single register instead of 2 independent registers. Okay, and for floating point, the vector processor use the flags and the routing mode for the FPU, and so it actually is shared between the floating point and the floating point. I mean the FPU and the VPU on the floating point operation. Okay, so the vector type register. So we have this is very important to understand. So the first parameter here is called the L mode, is the grouping of vector register. So the register can be basically the length of the vector register can be changed dynamically. It can be programmable, change dynamically. It can be 2x. So the VLEN can be 2x, 4x, or 8x, or it can be a fraction of the vector register. It can be 1/8 to 1/2. And so we will to detail of how this works in the next slide. And the SEU is the standard element width. And so for now, we basically will have 8 to 64. The other code is basically reserved for the larger size, which might or might not be used at later time. So basically, there are some couple bits that added in the later specification. And so, for example, and these 2 is the basically for the out order implementation. And in out order implementation, what happened is if you're using Raster renaming, so for example, the vector Raster A is renamed to Raster B, meaning that if you want to keep the same data, it means because of the mask. So if you want to keep the same data, you actually had to read vector raster A and write to raster B. So it meaning that you had to have an actual report for the raster file to read the data to put into the destination raster. And the actual report for 5 and 12-bit raster file is very expensive. And so there's an option that you not going to, if the element is masked, you're not going to update that element. And so you had the option to declare that the masked element can be unknown or undisturbed. Undisturbed, it means that you're not going to write the data. Unknown, it can be anything. But for verification, it's actually it's difficult, because say if you have an element is a mask, and you say it's unknown, and then if the mask become valid, now you don't know what is the actual data for the comparison at all, for verification purpose. So in reality, when they say agnostic here, you actually had to put in 0 or 1 in order to make it easy for verification. So in the vector process design, we have an innovative design algorithm which allow our out-order execution and completion without using any raster renaming at all. And so the result data is always written back to the VRF with or without a mask. And so the value of VTA and VMA actually have no meaning for us. The agnostic data is actually an undisturbed data. It's the same thing. And the last bit here is about illegal instruction. And so basically, like for example, we support only from 8 to 64. And if you try to set it to 128-bit, then it would be an illegal instruction. And so that illegal bit will be set, for example. Okay. Now, raster grouping. So for Elmo equal 1, you have 32 rasters, and each one of them is 5 and 12-bit. For Elmo equal 2, you only have 16 entry raster file, and 16 entry raster file, but each one of the raster now is 1K bit. When Elmo equal 4, there are only 8 raster in the raster file, but the width is 2K, and then for Elmo equal 8, the width is 4K. So this is a 4K bit, okay? But you only have 4. And so for Elmo equal 2, it means you have 16. It means only the even raster are used. And so if you have an instruction with Elmo equal 2 and an instruction, have an odd raster number, it means that it's an illegal instruction. And so for Elmo equal 4, the raster that's specified in the vector instruction had to be divisible by 4, otherwise it's an illegal instruction. Okay, and so the Elmo concept is actually very powerful, because if coupling with, because we have for Andes we have 128-bit to 512-bit, and the Elmo can make the raster become 4K bit, and so one single instruction can address an operation of 4K bit operation, and so again the raster width is configurable, and so we could design the raster width to 1K or 2K bit. So fractional raster, right? On the other hand, you can set the Elmo to be half or 1/4 or 1/8, and so only half of the element here, only 16 elements are valid. These elements are not valid at all when you have more equal to. And so the use case for it is that you load data into half of the vector raster, and then you can perform a vector double width operation to expand the data to the whole length. Or you can also load the data in, say, you load the data in at 8-bit, and then using a 4x extension to expand it out to 32-bit. And so that's one of the use case. Okay, and so the basic vector raster programming model, you have 5-bit, and VLEN is the width of the vector raster with power of 2. Actually, we start design from version 0.7, and at that time, the FPU cannot share with the vector raster anymore. So you have to have 3 independent raster files: scalar, floating point, and vector. And the vector, we basically had the elements start from 0 to the maximum number of elements depend on the width of the element. So if you have 64-bit element, then there will be 8 elements from 0 to 7. And then you have 32 that go from 0 to 15. And 16-bit, it go from 0 to 31. And again, it will go from 0 to 63 for the 8-bit element. And so the numbering, so now when you have L more equal 2, the numbering is actually very straightforward. You start from 0 to 63 and continue to go to 64 to 128. And similarly, you have the SAU equals 16, then it starts from 0 to go to 63, and the SAU equals 64, it starts from 0 to 15, okay? So now I'm taking the case of the 8-bit element with different Elmo. And so if you look at the Elmo equal 8, you have 512 elements. When Elmo equal 8, you have 512 elements. And this 512 element is actually the same at the width of the vector raster. And so because the width of the vector raster is 512 bit, and you have 512 elements, so every single bit of the vector raster can be used as a mask. So vector 0 can be used as a mask, and you have 1 bit of the vector 0 to control each one of the control each element in the vector raster. Okay, and so let's go to this. And so basically you had the mask. All the 512 bit are used when you have SAU equal 8. And so this is for the Elmo equal 1, only this one is used. For Elmo equal 2, then you have 128 bits. So only 128 bit is used when Elmo for the mask for SAU equal to 8, when Elmo equal 2. And then for Elmo equal 4, then you can use 256 bit to have 1 mask bit for each one of the element, or you can use the whole thing. And of course, when you go to SAU equal to 64, at most you can only use 64 bit of the mask raster. At most you can use a 64 bit only for that. And so 1 mask bit is for each element, as I said indicate, and 0 means the data is masked, and 1 is unmasked. It means that you are free to write the data back to the destination Raster. And so the mask is enabled in the vector instruction. So bit 25 of the vector instruction is reserved for mask. So if it's 1, then it's unmasked, and if it's 0, then you basically use a mask. And the mask is basically from the vector Raster is 0 when the bit 25 the instruction is 0. If bit 25 instruction is 1, then basically the instruction is unmasked. All the element can write the result back to the vector Raster. Okay. So now let's get back to this mapping again. Okay. So what happened is when the Elmo equal to 1, then you have 64 elements. So if you have a vector add instruction, it will perform all 64 8-bit add operation in parallel. But when Elmo equal 8, you have 512 elements. So it will require you to do 512 8-bit vector add. So 512 elements to be added. And so in implementation, if this will be for 512, it will be broken up into 8 micro-op. And so the vector processor will perform 64 element 8-bit add per clock cycle. And so you have 8 micro-op, so it can perform 512 element add in 8 clock cycle. And so the hardware will break up the instruction into micro-op. So Elmo equal 1 or Elmo equal 8, it's exactly the same instruction, except the hardware will know whether if it's 8, then it perform 8 micro-op. If equal 1, then it will be 1 micro-op. If it will be 4, then it will be 4 micro-op. Okay. And so as I said earlier, for example, you had a vector multiply operation. It will break up into 8 micro-op, and the first micro-op will write to V0, the second micro-op will write into V1, and the 8th micro-op will write into V7. And so the vector multiply is pipeline, so you can actually perform one at a time. And then you have a vector add instruction. And so in this case, the vector add instruction also will be broken up into 8 micro-op also. But because of the data dependency, and so as soon as the vector multiply is finished, it can forward the data to the add instruction immediately, right? So the vector add doesn't have to wait for all of this of the micro-op to finish before it can start. It can start immediately when the first micro-op is done. And so the data is being forwarded. And so this concept of forwarding data between the vector instruction when Elmo greater than 1 is called chaining. And so if you want to look at it another way, if Elmo is always 1, then there's no chaining at all. So chaining only apply when Elmo is greater than 1. Okay. And so, okay. Okay. The next control raster is the vector length raster, VL. Okay, and you can update VL with the application vector length. Okay, so vector length is the number of elements for vector operation. So if you look at the example down here, so in this case, the VL max is 32 and have 32 elements, and you can define the VL to be 21. it's more or less like a mask that you basically only have elements from 0 to 20 are the valid element that it will be updated on every vector operation, and element 21 to 31 are basically a mask, and so the vector operation will not update element 21 to 31, and so you can set the VL is the application vector length, and so when you update, so the VLEN is updated by the set VL instruction, and it is updated along with the V type. So this VSet VL update both the VL and the V type. And so the default for VL is the VL max. So if VL is set to be greater than VL max, then it's a default to VL max. Or if X0 is used for VL, then VL is set to VL max. And another way of changing VL is basically by using the for only first low instruction, which we will go to detail later when we talk about memory operation. And so when VL, well, if you set VL to 0, then basically no element update in the vector operation. Basically, it's like a no op operation. Okay, so let's look at the Vset VL I and Vset VL. So the two control and status register are updated by a single instruction. So you have two formats: one the immediate format, and one is using the vector register, so RS2, to update the control register. Okay, so the V type can be updated by using immediate data or using the RS2. So for V type I, the assembly name for the Elmo is basically from M2 to MF8 for fractional, and then the element size can be E8 to E64 for 8-bit to the 64-bit SEU, and then you can set in the tail element to be exotic or not, or the mask element. Okay, and so the default here, it basically will be, of course, Elmo equal 1, and the default here should be undisturbed. Okay, so the VL is set by using the RS1, and so if RD RS1, they're both equal to X0, it means there's no update for the VL. So do not write VL in this case. If the destination register is not X0 and RS1 is 0, then the VL is set to VL max, and actually VL max is going to write into RD. It is the same at the last case here, when RS1 is greater than VL max, then you do the same thing with the RS1 equal to X0. Else, basically you should take RS1 right into VL, and then update RD with the VL, the value of VL. Okay, so now we go to some interesting case for Elmo and SEU manipulation. Okay, so again, let's look at this instruction, the set VLI, and we set that basically the VL, because it's 0 here, so the VL is set to V16, And EA here is basically to set to SAU to go equal to 8-bit. And so you use MF4 here is fractional. And so when SAU equal 8-bit, the maximum number of elements is 64. But because you have MF4 here, it means that you set it to 16 elements. So this instruction is very important, the ZVL instruction, because we set it to 16 elements. It means all the vector operation had to be for 16 elements. So it always will be 16 elements. And so when you have this load instruction to load the data into V8, it will load only 16 elements. It will load only 16 elements. And so after that, you can do size extension of the 8-bit to 32-bit. And now you can change the SAU to 32-bit, and the default is the 1, and so the number of elements is still 16 elements, and so the vector operation will be for 16. The vector add is for 16 elements of 32-bit data. Okay, and so this one is what I explained before. Is that because the ZVL can be changed on the fly. So this thing had to be speculated. So the vector operation had to be basically using the speculated value of that based on the ZVL instruction. So it doesn't actually look at the CSR. It actually uses the speculated value for CSR. Okay, so now it's the same code again, but now set it to E32. So the SAU set to 32, L more 1, and you have 16 elements. And remember, this is 16 elements, so the operation will automatically set for 16 elements. And so when you do the vector load of the 8-bit element, it will only load, because this is set to 16 elements, it will load only 16 8-bit elements. Okay, and so it doesn't matter because this one VLE8, if you have VLE16 or VLE32, it's still always load 16 elements regardless of what the element width that's specified by the instruction. Okay, and then you can do the size extension, and again it will be for 16 elements, the size extend to 32-bit. And then you do the add, again, it will be operation for 16 32-bit element. So in earlier version of the 0.8 of the vector extension ISA, these two instructions, VLEA and VSEXT, actually was a single instruction, which is the VLB. And you load the data and do the size extension to 32-bit, and it's a single instruction. And so in the earlier version, these two instructions as a single instruction, so it comes down to 3 instructions instead of 4. And because we implement the vector processor since version 0.8, so we still had the implementation. So this VLB instruction can be a custom instruction within the vector processor. And we do have method to add custom instruction to the vector processor. You know, besides the load store instruction, we also have some other custom instruction that can be added also. Now, when we look at a large data set, for example, now we look at 128 elements. And so now we change the M8 or L more equal 8, right? So now you operate on 128 elements. And so when you do the load instruction, it will load 128 elements. But now, because 128 elements of 8-bit only need 2 vector raster, so it will put in V6 and V7 here. And then it will size extend the, again, it will size extend 128 to 32. note that all the operation here is on for 128 element because the set VLI here is set for 128 element. And so note here that because you use 2 vector raster, then even raster number had been used. So if this instruction use V5 or V7, then it will be an illegal instruction. And so when you do the side extension, there's a rule about the overlapping. So the source operand cannot be overlapped with the destination raster. And so if you use a source operand in V0, V2, V4, then it's an illegal instruction. V6, V7 are legal instruction because the vector raster are read before written. And so basically V6 is mapped to V0 to V3, and V7 is mapped to V4 to V7. And then the last control and status raster is the configuration. And so it basically is the VLEN divided by 8. And so this is a design time constant. It will be fixed and be set at the configuration. So you cannot change this this raster at all. It can only be read, but cannot be changed. And so, well, one more is the Vstar index raster. And this Vstar is basically used for exception. And so you initialize to 0. And so when you is the index of the element that causes a trap. Okay. So for example, if you load the data and you load the first 3 data is okay, and when you load the 4th data and you have an exception, and so you will set the Vstar to 4th element and take the exception routine, and then when you fix up the data and come back and restart to do the vector load again, then you will start loading data from the 4th element. That's where you had the exception and load to the end. And so after you do that vector load instruction, then the Vstar will be reset to 0 again. So the Vstar is reset to 0 every time you execute a vector instruction. So it doesn't matter what value it is, every time you execute it, it will be reset to 0. For any vector processor, only low store element can cause a trap and interrupt taken only the instruction boundary. And so if you have a compute instruction and Vstar is not 0, then it's actually an illegal instruction, or we will take exception for that case. And so if you look at the valid range for all the data element, so the example here is that if all the elements before Vstar are not valid, its star valid is on, basically from the Vstar. And on the other end of the spectrum, the VL, it basically indicates where is the last valid element that you have. And then the mask element can be masked out, right? So you can have the mask element that basically say not to update 10, 16, and 20. And so when the vector operation, when you do the vector operation, it only update the valid element that are in green here. All right, so that's it. Thank you everyone for attending.
Thank you, everyone. See you next time.
Okay, bye-bye.
Bye.